Good morning. Today we will start our discussion with processing of images. Uh, while discussing the various steps at the sensor level, how the energy that is coming from the ground resolution cell that is sensed at the sensor, then further that energy is processed to generate a digital number. And the last stage is the color assignment. Like when we display the image on the computer screen, so corresponding to different grid cells, how we can see a particular color. So uh, till that steps we have done the discussion. Now in satellite image processing, before discussing the various algorithms, first we will discuss how images are formed. Like when in a multispectral band, digital numbers are acquired from the scene, and when we display it on a computer screen, how we can see visualize the single band image as well as multi-band image. So for the single band image, we have already discussed how a particular set of gray color is assigned to a digital number. So at the so if you see the color assignment as a type of transfer function, so it can be explained by the two-dimensional graph over here, where on the independent axis, we place the digital number values, and if image is 8-bit, so we have a range from 0 to 255. On the dependent axis, we put different sets of gray color that vary from black to white. So at DN0, we assign black color, and at DN255, we assign white color. And the transfer function that we use for this color assignment is linear in nature over here. So in between 0 to 255, let's say if there is a certain DN number at 45 or at, let's say, 180. So by using this linear transfer function, when you connect it over here, so this particular set of gray color is given to the grid cell. Okay, that particular grid cell is shaded with this set of gray color. Okay, and when that cell is having DN 180. When we come to the multi-band images, so you know that we have a three primary colors: red, green, and blue. So to see the image, to see image in color version of the image on the screen, at least we require three spectral bands at a time. Okay, and let's say in a particular satellite imaging system, the n bands are required. There are n spectral bands, and in n spectral bands, images are collected in the form of digital number. Okay, so out of n, to see image in color version, okay, we select three spectral band at a time, considering we have only three primary colors: red, green, and blue. So we have a three color guns, okay, corresponding to red, green, and blue. Okay, so these three color guns are used to assign color to the digital numbers when three bands are selected. Now, based on the mm, magnitude of these colors, they are mixed together. Okay? And after the mixing, we get a color pixel. So we'll see, like by analyzing the color cube, how by mixing red, green, and blue in a different proportion, various colors combination can be formed. Okay. So till now in our discussion, we have seen that uh, single band image, we can display the image either in a grayscale format or in the color format. Okay. When we consider the grayscale version of the image, then we select one band, okay, and corresponding to the digital number, we assign different sets of gray color. So this will be a single band image, and we visualize it in a its gray version. Now, when we consider the color image, so to form the color image, we require 3 spectral bands, and each spectral band is given 3 primary colors. Okay, out of 3, each spectral band is allocated to one of the primary colors. And the primary colors we have red, green, and blue. So in this way, we form the color image corresponding to the satellite images. In this case, you can see that we have 3 cubes, the 3 spheres, okay? And they are projected over here. So they are seen as a square. And there are the overlap region. This is the overlap region over here. In the overlap region, all 3 colors are mixing in an equal proportion. So in a color, by using the color guns, the color guns, let's say if we consider for red, okay. So at a different strength of red color, the color guns generate it, and it is generated on the basis of magnitude of digital number. Okay. In 8-bit image, we have a 0 to 255 DN numbers. Okay. And let's say in a given spectral band B1, for the given spectral band B1, the selected color gun is red gun. Okay. So on the basis of magnitude of digital number, the strength of red color is generated from the color gun. Okay. Similarly, as I said before, for the formation of color images, we require 3 spectral band, and each band is assigned to one of the color guns corresponding to red, green, and blue. Similarly, if we select second spectral band, that is B2, and we are assigning the green color gun to it. Okay. So on the basis of what is the strength of DN numbers in band B2, strength of green color is generated from the color gun. As you see in this case, the intersection region where red, green, and blue, all the colors are mixing in equal proportion. So when they are mixed in equal proportion, the white color is formed. While in the 3 other cases, like when we mix green and red in equal proportion, then yellow color is formed. So yellow color is a yellow. Then we have a magenta and we have cyan. So these 3 colors are secondary color when 2 primary colors are mixed with mixed in equal proportion. So for the elaborated discussion will be done on the basis of color cubes, where you see we assign red, green, and blue color along on 3 axes. Okay, and further on the same axis we mention the digital numbers, and we'll see within the cube, and within the cube the concept is given like if there is a combination of 3 digital numbers from 3 spectral band, okay, what color will be there, that will be seen. On the basis of combination of spectral band and color guns in terms of 3 primary colors, we categorize the color this images into 2 form. In the first case, it is 2 color composite, where 3 primary colors, they are assigned to the same color. They are assigned, let's say we consider red spectral band. So when the red color gun is allocated to red band, so there is a synchronization between the actual color and its wavelength that is given in the spectral band. So if the wavelength in the spectral band is same as the color, the wavelength of color gun we are talking about, okay, then in that case, if these combinations prevail for all the spectral bands, obviously for the color this color image formation we require 3 bands. Reason is that we have only 3 primary colors, so we can't go with more than 3 or less than 3. So fixed 3 number of spectral bands are required. And further, we'll see the combination like out of 3 red, green, and blue, which color gun we are assigning to the spectral band. If there is a synchronization in terms of like if we select a spectral band in red, to same wavelength color is if it is allocated, and this will remain for all 3. So red for red, uh, red spectral band, red color gun is assigned. For green, we assign green spectral band, green color gun, and blue spectral band, we assign blue color gun. This is called as 2 color composite, and it is photograph. Okay. So if we discuss about our own vision system, so our own vision system, our eyes follow this combination. Like our eyes sense the energy only within the visual spectrum, and red, green, and blue. And once the energy from these 3 spectral bands are sensed by eyes, the color assignment is synchronized. Like the red color is given to the red spectral band, energy sensed in red band. Similarly for green and blue. So if this is the combination, the image that is formed is called as photograph, and it is 2 color composite. Okay, photograph means how our eyes see the object. If same color is there in the image, then it is photograph, and this combination is followed. While any other combination is classified as false color composite. If you deviate from this combination, okay, and for any other combination, it is termed as false, this FCC, false color composite. And one example is given over here. Green band, if we assign red color to the green band, then obviously other combinations will change. Then blue to green and red to blue. Okay, so in this case, this become FCC. Okay, In case of Indian remote sensing satellite 1C, there are 4 bands, 4 list band, and these spectral bands are selected in green, red, IR, and mid infrared. So we don't have blue band over here. And so when you click the image to see it on a monitor, then what happens? The color guns will be activated, okay? And they pick the spectral band for the color assignment. But as you have already seen in the laboratory experiments, you need to choose, like if we have 4 bands, so first you need to select out of 3 bands for the color image formation. And further, you also assign which color gun you want to associate with the spectral band. Like in this case, if it is band B1, it is green band. If it is allocated to the blue gun, okay, and the band B2, it is green, and B3, it is red. So in this software, this is done by the user. So provision is given in the software, as you have seen uh, in the software you are using in the laboratory. Okay? So there is a provision to assign color to the particular band, and finally you will generate the image. Now just see over here, 2, 3, and 4. The 3 bands are selected. Band 2 is green, while band 3 is red, and band 4 is NIR band. Okay, and blue gun is given for green band, while the red spectral band, uh, green color is assigned, and for NIR, red color is assigned, and the image is formed. But this is not a photograph, this is false color composite image. Can you analyze the types of object which are present in the image on the basis of known fact? Like in this case, the known facts are, you know that while the while the assignment of different guns to the spectral band, what is the combination that is followed? In this case, 2, 3, and 4. Band 2 blue, band 3 green, and band 4 red. Okay, so 2 is green, and this band 3 is red, and band 4 is NIR. Can you tell me the red color is representing what kind of object?
Vegetation.
Vegetation.
Why it is vegetation?
Sir, because NIR band is reflecting more for vegetation. And
Yeah,
yes.
All of you are correct. If you refer this discussion over here, so I told that how we assign a different strength of color, how the color gun generates the strength of that particular color. Okay, so in NIR band, like in this case, uh, uh, I told you to guess the type of objects which are represented by red color. Okay, so information that is available with you is red color. So there are red pixels which are there in the image, and we need to know that, and we should just see that, like This red pixels are representing what kind of object. Okay. So from the given information, first you need to see that red color is given to which spectral band. So the red color, that is fourth one, it is given to the NIR band. Okay. So now see, so it is given to the NIR band. Okay. If out of red, green, and blue, pixel is represented by red color, it means other two colors strength is very low, and the highest strength is given to the red color. On the basis of this discussion, where I told that 0 to 255, if we consider the 8-bit image, and if let's say band B2 is given green color, so strength
Sir,
of green, yeah, please.
excuse me. Sir, how we came to know that the strength of NIR band that given to the red band, it is more than others.
That point I'm discussing over here.
Okay, sir.
Okay. So just wait. Okay. We can discuss from this color cube uh, along the three axes. Green color is given to the x-axis if I mark it, and the red color is given to y-axis, and blue color is given to the z-axis. So red, green, and blue, better to follow the convention over here. So x, y, and z. Okay. Now along the same axis, if I talk x-axis, so x-axis retain two information. The first one is the distal number, and while the second same axis retain the different strength of red color. Okay, so these two information overlap on x-axis, and just see how it is decided. The least strength of red color if it is 0, and highest strength of red color if it is 255, and it is given on the basis of, let's say, from draw a line over here, and this is 0, this is 255. Okay, in the linear way we assign a strength of red color, so darkest, and this is lightest. So least strength of red color over here and highest strength of red color will be given 255. Fine. So this is the representation on the various axes. Okay. Now what we need to do, like in the previous case, we see most of the pixels bright red in color. Okay. So there are many pixels which are scattered in the image and they are bright red in color. Okay. Now we start our analysis in a backward direction. So first we see the red color gun is assigned to which particular spectral band. So that we can get this information we can get from the processing step. So while the color assignment, once you assign a color to a particular spectral band, so you know that red color you are assigning to NIR band. So this information is available. Now come to over here. This red color is given to NIR band. Fine. What this indicate? Red color is on the x-axis, and the 0 to 255 that we are digital number we are talking about. These this digital number is collected in NIR band. I hope it is fine. Okay. Now, if it is dark red in color. So dark red in color, if you see the mixture of color over here, okay. So you will get dark red in color only in the case, like if again, when the strength of red color is dominant compared to blue and green. Okay. How it will be dominant compared to blue and green? When the strength of blue and red is very less. In this case, if there is dark red color, it means the strength of blue and red, the strength of blue and green, they are very less. Again, see these axes. Uh, this is the green axis. So when the strength of green color is less, it means somewhere here we are talking about. Okay. So for this particular green color, the distal number which is there is very less. Similarly for the blue. Okay. If the strength of blue color is less, okay, if the strength of blue color is less, it means the distal number corresponding to that pixel is very less. Okay. And red is dominant, means somewhere in this range, the distal numbers are coming for that NIR band. Okay. So 0 to 255 in this case, just you need to see over here. The green band is for which one? The green band is given to the red. Okay. So this is for red. Okay. Yes. On this axis, we have a red spectral band, while on the blue, we have a green spectral band. And on the red, we have NIR spectral band. Okay. Now we have seen that on the basis of color, in which particular range the distal numbers are corresponding to that color. Okay. So dark red color indicate very low strength of green and low strength of blue. It again suggests like the distal numbers in red spectral band lying in lower side, while the same case is there for the green spectral band. So in both corresponding to those grid cells, like if I select one grid cell over here, okay, and for this grid cell, what is color? Color is red. So now we will see for that corresponding to that grid cell, what are the distal numbers which are recorded while the image acquisition in green, red, and NIR band. For red band, they lie at the lower side. Similarly, for the green spectral band, they lie at lower side, while in NIR band, they lie at the higher side. Okay. Now, at the level of DA number, at the stage of DA number generation, you have decided the range of what could be the probable range of distal number corresponding to the grid cell that is painted by red color. Okay, so the red painted grid cell we have derived over here. By the way, tell me one thing over here, like when I talk about three spectral band over here, so corresponding to one grid cell, how many digital numbers are generated? Like what is the like if we represent a digital number by vector, then what is the size of the vector?
3x1.
What it will be?
So 3x1.
Sir, each band के लिए one DN value.
Okay,
Blue
for
field.
one band, one digital number. So if the DN numbers are represented in a vector, obviously if we have a more than one spectral band, so DN number representation will be in the vector format. And the number of rows, if we have a one column, then we have a n number of rows where n indicate the number of spectral band. So while in this case, we have selected only three spectral band to form the color image. So it is represented by 1 cross 3 cross 1 vector over here. Okay. And at this place, we have DN corresponding to NIR, is it? Then DN corresponding to red. And the third, we have a DN corresponding to green spectral band. So what we will do, we will further back transform it in a backward direction. So digital number corresponding to NIR band. So there is a energy collected at the sensor in NIR. Similarly, there is energy collected at the sensor in red band, and here energy collected at the sensor in green band. Okay. So the generation of digital number from the energy collected at the sensor and their relationship is directly proportional. If energy will be large, okay, then the corresponding digital number magnitude will be high. That we have seen. Similarly, for other two cases. On the basis of color you see in the image, we have already concluded where the digital numbers are lying in this color cube are between 0 to 255, at which particular level the digital numbers which are representing this red color, where they are lying. For these two, red and green, the digital numbers are lying at lower side. It means the energy will be less. The energy that is generated from the energy that is generated from the grid cell is very less in red and green band. Is it clear? This conclusion we can draw from this analysis. When the DN number in red and green, they are at lower side, and this has been decided on the basis of strength of color in green and blue. If red is there, then strength of green and blue is less. It is less because on this basis, if you see the color assignment, the strength of color is assigned linearly on the basis of the magnitude of digital number. If magnitude is high, the highest strength. If magnitude is of low, then lowest signal. I mean the lowest level of color from that particular color gun. On this basis, we have arrived at a conclusion: low DN number for red and green band So low energy at the sensor from red and green. And finally, we can conclude that there is a low level of energy that is outgoing from the grid cell in red and green corresponding to NIR. While in NIR, we have a highest strength of the energy component in NIR band. Now we will analyze by seeing the spectral signature of various objects. We have already discussed the spectral signature of vegetation, water, soil, snow, concrete. Okay. When you see the spectral signature talks about how efficiently the object is reflecting the energy at a different wavelength level. Okay. So by analyzing the spectral signature of these major objects, you will see that in case of vegetation, in NIR band, the reflectance is highest. Because if you refer the soil, you can't see much change in the reflectance. It's a gradual increase. The spectral, if you analyze the spectral signature, the reflectance curve is gradually increasing from visible to NIR to mid-infrared. Okay. And while if you analyze the spectral signature curve of vegetation, so within a visible, the highest peak you will get at green. So there is a sharp valley at the red band. And after that, there is a sudden jump in the reflectance when you move from red band to NIR band. Okay. And in NIR band, up to the certain range of wavelength, there is a reflectance more than 40 to 50%. Okay. So from this analysis, we can say that, okay, in NIR band, the energy that is coming from the grid cell is highest in NIR band. So there is a possibility like this grid cell is from the vegetation. This is a processing step to arrive at this conclusion. So if it is a kind of subjective problem, like an image is given and it is asked to just predict a particular color pixel belong to which object, so you need to explain in this way. So this entire process you need to adopt. First, you need to draw color cube. Okay, on the color cube, you need to map. Okay, like the color gun and distal number from a spectral band. And then in a backward direction, you need to arrive what is the energy reflected from the grid cell. Okay, so once we visualize the image on the computer screen, so can we go with the manual interpretation? Like ultimately, our aim is to identify the objects as well as just see the differences, like how we can classify the object for various scientific and industrial applications. Okay, so processing of image for identifying the object, classifying the object, it can be done manually. Just you open the image and just see it. The processing in terms of object identification and classification, it will be easy if we see the color as a photograph, we see the image as a photograph. Okay, but if we are visualizing manually the image in FCC, okay, then we should have idea about this entire analysis. Because on the basis of this analysis, we can conclude, like if we see a particular color pixel, that pixel represent which object. Okay, but there are many limitations in manual image interpretation. Okay, and due to which it is not a feasible approach for images related applications. And this creates scope to go for automatic processing of images. Okay, and that comes under the scope of satellite image processing. That part we'll start discussing later. So we have the limitation there which are listed over here. It is very accurate because if you see a very small area and if you see the photograph, you can clearly able to distinguish on the basis of your perception. So it is accurate, but only for the limited data. Like in this case, very clearly you can bifurcate the pixels which are from the building, and trees pixels, road pixels, vehicles are there. Very small size images there, and analysis can be done very accurately. But if let's say we have a very large area in few square kilometer, then it would be difficult to go with a manual interpretation. Now it's because in that case it will be very time consuming, and no repeatability. Like once you do it, you can't store it. Like by using the computer system, if you process the image, at least you can store the result. And if you go with the second level of processing, that second result can be separately stored. While and that creates the facility for repeated analysis. But it is not possible in manual interpretation. And manual measurement will be difficult. Large storage of data, it can't be done. It is not feasible. And it is very difficult to transfer data and result in hard copy format. Because once you analyze, you need to make a drawing for that. While using the machine, if you do the processing, the result can be taken can be taken in the hard copy format. If we have a more than 3 bands, it is difficult to take into the account. Like we can do the analysis only by visualizing the image, while the machine can do the analysis on the digital numbers. That is the actual information that is stored. So these limitations creates scope to go with digital image processing, where image interpretation and measurement is done by developing the algorithms and processing them through the computers. How computer understand an image? Like computer process the image data in a binary format. And you know that each grid cell is assigned a digital number and its binary version is stored. And that and actually this image, the image that is stored has only array of digital numbers. How computer can understand? This analysis will do. In this image, you can see different color composites. Like by mixing a different strength of digital number, how colors are formed. In the third case, if you see that, when red, green, and blue colors are mixed in equal proportion, we form different sets of gray color. Okay. As I discussed before, how computer can understand the image, because the image data is having only the digital numbers. Okay. So to understand the image, certain statistical analysis is performed. And here I am considering the multi-band images where n represent the spectral band. So what we do by selecting each band at a time, we do certain analysis to compute the statistical parameters like what is a mean, what is a minimum value of distal number, maximum value, mode, median, okay, etc. These parameters are computed spectral band-wise. Out of n band, we select one particular band. Let's say B1 is selected. It is in red spectral. It indicates the red spectral band. What we do, we see the size of image, and in the image space, it is represented by I comma j. Like if you see the image, so in two dimension image is represented by, let's say this is I and this is A. So first we see the size of the image in terms of how many grid cells are there. If I varies from, let's say, 1 to n and j varies from 1 to m. So how many grid cells are there in the image? They are n cross m. Okay. N cross m numbers of grid cells are there in the image. And for each grid cell, we have a distal number dn I comma j. So these information is for the single band image that is selected in red band. It is for band B1. What you do next? By writing some computer code, you can calculate what is the minimum DN number and what is the maximum DN number. It can be done. Mode can be calculated, the most common value obtained in a set of observations. Similarly, if you sort all I comma j, it means you can say how much it will be. It will be 1 to n cross m. So out of all these distal numbers, you just sort them in increasing or decreasing order and you can calculate the median. You can measure the mean value. X is the distal number corresponding to ith position. Let's say I comma j. We can replace it by only one index I. So in that case, I varies from 1 to n cross m. So here I varies from 1 to n cross m. In this case, n is a total number of grid cells. So mean is calculated by taking average of all distal numbers divided by total number. Similarly, you can calculate the standard deviation. Okay. And we can also measure the variance. These parameters are calculated for each individual band. We can also analyze the relationship between multiple bands. Okay. And that relation is estimated in terms of covariance and correlation coefficient. As we are talking about total n number of bands, in which we are collecting the image. Okay. So out of n band, for each band, we have calculated these parameters. Now we see the relationship between pair of bands. Out of n band, what we do, we select two bands at a time. Let's say this is X from band B1 and this is Y from distal number from band B2. So B1 and B2, we calculate a covariance. Okay. Similarly, we can calculate the correlation coefficient between band distal number X from band B1 and distal number Y from band B2. And it is given as covariance of band B1 and B2, and what is the standard deviation of band B1 and B2, you multiply it. So you will get correlation coefficient. Can any one of you tell me, there are n band, how many covariance we will generate? If n spectral image in n spectral bands are given, okay. So how many covariances we will generate? Rahul Kumar, could you please unmute?
So n minus 1.
Did you understand the query?
सर कोवेरियंस अगर n बैंड्स हैं सर तो कोवेरियंस कितने होंगे ना सर?
हाँ, जैसे टोटल नंबर ऑफ बैंड n है,
यस सर.
तो सारे बैंड का यूज करते हुए हम कितने डिफरेंट सेट ऑफ कोवेरियंसेस कैलकुलेट करेंगे? बिकॉज टू कैलकुलेट वन कोवेरियंस वी आर यूजिंग टू बैंड. To generate one covariance, we require two band. So out of n band, how many covariances we will generate? It will be equal to how many band combination we can form using n band. Taking two band at a time, how many combinations we can form using n band? So what it will be? It will be NC2. Fine.
Yes sir.
Why we can't say it in terms of permutation? Why not we write it NP2? If you remember the covariance, if you change the location, like at this place keep B2 and B1 shift to the another place, what it will be? It will be covariance between Y and X. There will not be a change. So covariance of X comma Y is equal to covariance of Y comma X. So it is the same, it is not a different. So this is the reason why we do not say in terms of permutation, it's combination. So NC2 will be the total number of variances, unique variances, which are computed using n band. Okay.
Yes sir.
How many correlation coefficient we will get? Correlation coefficient, again we are using two band.
Yes, same NC2 sir.
It will be NC2. Okay.
Yes.
Please mute. After calculating these parameters, where we are considering the information from two bands, okay, finally we design a variance covariance matrix. Okay, and this matrix represents the entire information in a given image. Okay, so if the given image is in n band, okay, so by analyzing the distribution of distal numbers and their relationship between two bands, variance covariance matrix is formed to have a overall representation of the image. So let's say if we have a n band, What will be the size of variance covariance matrix? Who will tell me?
Sir,
In
n
the
cross n.
invariance covariance matrix along the diagonal axis, okay, along this diagonal axis, we keep the variances, while the off diagonal elements are covariance. So the size of variance covariance matrix will be n cross n. If n is a spectral band, and they are represented like 1, 2, 3, 4 till n. Similarly, 1, 2, 3, 4 till n. And if you see along the diagonal axis, in each band, the variances which are computed, okay, they are placed over there, while the off diagonal elements are covariance. Okay, and the variance covariance matrix satisfy the mirror image if you consider the around the diagonal axis. Why it is so? Because sigma 2 1 is equal to sigma 1 2 that we have seen over here. Band 1 and 2, if you calculate the covariance between band 1 and 2, it is same as covariance between 1, 2 and 1. Like in this case, covariance y comma x is equal to covariance x comma y. So this variance covariance matrix is mirror image around the main diagonal axis, where the variances are placed. When we started our discussion, there we talk about selection of 3 band for the image formation. So which 3 band we need to select for the image formation and for the visualization of image for its analysis? So if we have a n number of bands, okay, which are more than 3, for the color image formation, which that is followed by image interpretation. So which 3 band we need to select out of n? It is again decided on the basis of how many information is retained by each 3 band. Okay. So how many, first we see how many FCC combination we have. So n band combination is 3. By taking 3 at a time, we have a NC3 total FCC combination, and one combination we need to select for the image formation, color image formation. And it is decided on the basis of computation of optimum index factor. And OIF tells us in which particular combination the information contents are highest. And OIF is calculated summation of standard deviation in each band. Okay. Each band means we calculate OIF for each combination. So band I is equal to 1 to 3. Sigma I for the selected 3 band, we calculate it will be equal to sigma 1 plus sigma 2 plus sigma 3. If let's say band combination is B1, B2 and B3, where I varies from 1 to 3. Okay. So it will be sigma 1 plus sigma 2 plus sigma 3 divided by, this is correlation coefficient between these bands. What you would do, R12 plus R23 plus R31. Similarly, by changing the index value I for the band, you calculate OIF for all the combinations. And the highest OIF that you get for a particular combination So that combination will be used for the interpretation, or that combination will contain the more information content and the lowest amount of duplication. Okay. So I'm giving you 5 minutes time to kindly make note on this discussion, and we'll resume our session again at 12:16 p.m. Okay, so I hope you have met note on the discussion. To analyze the image statistically, we calculate various parameters as we discussed before, and those parameters are specific to the single band, and some parameters are specific to the combination of two band. Now we have a further analysis to analyze the image. We do it in terms of generating the image histogram. Okay. Let's say we have discussed over here the total number of grids in the image, and corresponding to each grid we have a DN number. So if rows and column, they are n, if there are n rows, that is given by index I, and they are m column, that is given by index j. Total number of digital numbers are n cross m. So these DN numbers represent total n cross m DN numbers. They represent different values of digital number, and they can be plotted in terms of frequency distribution with respect to the magnitude of digital number. Frequency distribution, let's say if we select one particular DN number, it is 45. Okay, so what we do, the algorithm which you develop for histogram generation, that algorithm will search each pixels in the image. In the single band image, one by one, each pixel is searched to match with DN45. Okay, and the number of match that will be there in the image, it will be the frequency of DN number 45. So this will indicate how many times the DN45 occurs in the image. So it will be given a value that tells us the repetition of DN45 in the image. Similarly, for all other DN numbers, their repetitions are calculated and they are plotted in terms of, and this is called as image histogram. Okay, so our mind is excellent at interpreting the spatial attributes of an image. Okay, and our eyes is poor at discriminating the slight radiometric or spectral differences. The spatial attributes, when we see, we can analyze the changes in a spatial domain from one location to another location, but we can't distinguish the changes in radiometry or spectral differences that is recorded in terms of energy that is received from different grid cells. Okay, so to do that, to improve the discrimination, what we need to do, we need to go with image enhancement. By doing the image enhancement, the poor discrimination between poor discrimination of slight changes, radiometric and spectral changes, can be further enhanced. Okay, for the better discrimination. To go with image enhancement techniques, there are two operations, two types of algorithms we have. The first one is point operation, and the second one is local operation. In case of point operation, what we do, we modify a pixel value independently by processing it a certain steps of an algorithm. While in case of local operation, we modify the digital number of a pixel by considering its own value as well as the value of surrounding pixels. In this case, it is one-to-one operation. Like one particular pixel is selected, it is processed through a equation or an operator. Okay, and further its modified value is its modified value replace the original value. While in this case, pixel is selected, it is modified considering its own value as well as value of surrounding pixels, and it is processed through operator to change its original value. So this is the difference why we call it point operation. Only one pixel is selected. In local operation, that particular selected pixel and its surrounding pixel. And this image enhancement can be performed single band wise, or it can be performed individual component of multi-image composites. We do the image enhancement to improve the visual quality of image. As I said before, our eyes are poor in discriminating the spectral and radiometric differences. So by applying image enhancement, we increase the differences so that it can be identified in a better way. So the difference can be distinguished or it can be discriminated by our eyes. So we just highlight the differences. And the aim is to enhance the slight difference in radiometry of image for visual inspection. No any information is added in this process. Okay, it's just a modification of digital numbers in the original image. These enhancement techniques are classified into three parts. The first one is contrast manipulation, that is performed using histogram, and we call it point operation. The second one is spatial feature manipulation or multi-image manipulation. They are done using local operator. In a point operation, by using the histogram of the image, we can do the processing, and one of the algorithm is binary masking. This is the histogram of this single band image. Okay, where we have two dominant colors, white and black, and it is visible in the and it can be seen in the histogram. So in the histogram, there are two peaks, and we have a two major object. Okay. So to improve the quality, like in terms of only two object we have, let's say we want to see how much area is covered by each object. So there is a black background and there is a white color object on the black background. So what we can do, we can go with a binary masking. This histogram is given, and let's say the range is 0 to 255. 0 to 255 means the pixels in this image are represented by 8-bit. So we have a total 256 digital numbers, and they are ranging from 0 to 255. And similarly, 256 shade of gray color is assigned over here. Objects are only two. So we can reduce the even size of the image. Okay. And we process it. It can be done. This is the frequency over here. What we do, by identifying these peaks and the valley, we select this is a threshold DN number. DN threshold is selected on the basis of histogram. Like there are two peaks, and in between two peaks we have the valley. So the first peak and its surrounding DN numbers represent one object, while in the second peak and surrounding DN numbers represent second object. So we go with the thresholding by selecting a DN threshold. And what we do, let's say for all digital numbers, now the function that will be generated, it will be 0 for DN minimum less than DNI less than DN threshold. It means this is the minimum digital number to DN threshold. In the output, let's say if this the IF is used over here to represent the frequency, so it can be given, let's say capital F. So value of F is selected 0. For this 0, output will be for all these digital number we assign 0. While the DN threshold to 255 we assign 1. And now this is the, after this processing, this will be the generated image. And for this image, this will be the modified histogram, where we have only two digital number. They are 0 and 1. Actually, this is 1-bit image. 8-bit image is converted into 1-bit image. If we have more than 2 objects in the image, okay, and if more than 2 object we have image, again we extend the same methodology for the level slicing. Let's say we have 5 major objects which are present in the image. And this is the histogram. 5 major objects, we have 5 peaks. And they are again 0 to 255, and this is the frequency. What we do, we decide these thresholds. 4 different thresholds we will get. And what we do, for the first case, we assign 0. For the second, 1, 2, 3, and 4. Okay. This is called as level slicing. Now 8-bit image is converted into less number of bits. Like here we have a 5 distinct decimal number. So how many bits are required? We require 3 bits. Okay. It can be also seen in this way. If let's say it is given, so we'll assign 0, then level 1, 2, 3, and 4. So this is DN input. It is given to the algorithm of level slicing, and this is DN output. For all these, what we have value 0, we have value 1, 2, 3, and 4. Similarly till M. Okay. So it is combined, like lumping together. What we are doing, all these digital numbers we are lumping together to assign a single value. So different values within a specified range are interleaved into a single value and displaying them by colors. When we assign 0, 1, 2, 3, and 4, we assign them a color. So we have seen that how we can convert an image into a modified version by reducing the number of bits which are used. And it is done by analyzing the histogram. We further do the histogram manipulation, that is also called as contrast stretching. First, we will see why we go with histogram manipulation, why it is required. In case of 8-bit image, the display image display uses full range of 8 bits which are there from 0 to 255. But sensor may not capture this entire range, though they are capable of. And it entirely depends on the scene brightness. If you do the analysis, statistical analysis in the image, let's say if we select band B1 in red spectral band, okay, and n cross m pixels are acquired while calculating the statistical parameter. It is again, we consider it 8-bit image. When you calculate dn mean and dn max, so the full range that is available is 0 to 255. But in most of the images, what you can see that when you calculate dn mean and dn max, they are not 0 and 255. They are somewhat at higher side or lower side. So there is possibility, for example, let's say minimum digital number comes out to be 45, while the dn max comes out to be, let's say 230. So in this case, what you are analyzing, 0 to 245 is not used. The full display range is not utilized. For this example, 0 to 45 and 230 to 255. These DN numbers are not used in the image. So image digital numbers are only confined between 45 to 30. What we do by manipulating the histogram, we stretch the image such that 0 to 255 and 230 to 255 are also incorporated to represent the image, so that we'll use a full display label that is available. And it will further improve the radiometric and spectral differences in the image. And this is shown in this example. In the given image, when you plot the histogram, the mean is 60, max is 158. The available range is from 0 to 255, but the utilization is only between 60 to 158. Okay, so what we do, we stretch the histogram of image such that the pixels which are given DN number 60, after the linear stretch, they are given value 0. And while which are given 158, they stretch to 255. Just see what is happening. In the previous case, this is the difference between digital number, but while stretching, the difference is increasing. Okay, and this is called as the radiometric and spectral difference. See, the difference in digital numbers is called as radiometric difference. Okay, ultimately this is a difference in energy that is coming from the cell. And there are other types of stretching algorithm like histogram stretch. In this way it is done. And there are certain special stretch that we'll see. But linear stretching is done in this way, and we can derive the equation for this. For the same problem, this is the for dn input. We'll see. For the dn input, the value is from 0 to 255. Okay. In the image, minimum is 60 and maximum is 158. So this range is available in the image. What we want, by using a linear transfer function, that is given over here. Okay. All these digital numbers are transformed. So to see how it is transformed and which equation is followed for this transformation, we can do the derivation over here. 60 is given digital number 0 as you see in this transfer function, and for 150, 255 is given. So if you see 60 is assigned 0, and when this another peak, it is given 255. What we do, we calculate, and this is DN output, we'll say. DN input 60 to 158, while in DN output we have range 0 to 255, and this is DN output. We just derive the equation that is used to transform DN input to DN output in a linear way. So this will be given by this equation of this line. Okay. So we have a two known points. Line of the equation can be calculated. So what it will be? It will be 60, 0. Let's say this is point A and this is point B. It is given as 158, 255. Okay. And even you can start y is equal to mx plus c. How we calculate c? C is the intercept. X is equal to 0, then what is the value of c? Or even you can write it y minus y1 is equal to slope m x minus x1. Okay. And what will be the slope here? Y2 minus y1 divided by x2 minus x1. So the equation comes out to be like when I consider 158 as a dn max. If just I write it max, if maximum distal number is represented by max and minimum is represented by mean. Okay. Then this will be the equation by solving the straight line. dn dash is dn output is equal to dn minus mean divided by max minus mean into 255. So what you need to do, how it is processed? We have a m rows and n columns. So m cross n is the total number of pixels. One by one, each pixel is selected and substituted over here, and corresponding output value is generated. This is one way to do it. And another way is to go with a lookup table. This is very important to understand. Like the first one is select each pixel, process through this equation and generate the output. And the second way is to go with a lookup table. It is just searching and replacing the value. How they are different, it can be explained here. So the equation that is generated, what we do, we already know that what is the range of DN input. So DN input range is from, if you say DN input is from 0, 1, 2 till 255. Okay. Now we have derived an equation that is DN dash is equal to DN minus minimum divided by max minus mean into 255. Okay. We know what is the range of DN input. This is 0 to 255. What we do one by one for each digital number, we select a DN output. We calculate the value for DN output. Okay. So what do you do first for the given image? Just see what is the DN mean, what is max, and derive this equation. And after that, using that equation, generate a lookup table. DN dash is equal to DN output. For the given image, first what you need to do, you need to calculate the maximum digital number, and then you need to calculate the minimum digital number. These two statistical parameters can be calculated. Let's solve this equation. After solving this equation for all the values of digital number for 8-bit images is 0 to 255, generate a corresponding DN output. And after that, what you need to do, for given M cross N image, select, let's say you select DN45. Okay. So corresponding to DN45 in the table, just search it, what is the DN output, and just replace it. It means you are not passing to this equation. The lookup table is already generated, and now you are just searching, and you see the match, and just you going to replace it. This method is computationally efficient. Let's say when the size of image is very large. Let's say M cross N is some 10 to the power 5 pixels. Okay. For these number of pixels, if you adopt the first process, then what you need to do for each time, you need to pass through the DN input over here and generate DN output. And this equation needs to be solved each and every time. This will be the computationally inefficient way to do it. Better way, you have already generated a lookup table. Only 256 times you need to solve this. Now you have a table with you. Select a DN number corresponding to each pixels. Just see, search them, replace the value. So lookup table based histogram manipulation is a time efficient way for the large image. But let's say if image size is only 25 pixels. There are only 25 pixels. Then obviously you need to go with the first method. Like there is no need to generate solve for entire 256 pixels. So in that case, for only 25 pixels, I used pass these pixels through this equation and generate the output. So we have covered the first method of image enhancement, and that is the point operator, where we select one pixel, we process it to a particular algorithm, and we generate output, and we replace the original image by the modified values. And the objective is to improve the visual quality of image. Like in the contrast enhancement, by increasing the differences between two pixels, you are improving the quality of image so that it can be differentiated radiometrically. So radiometric differentiation can be possible by increasing the difference between the neighboring pixels.